We now go over the integrated rate law. Let's consider a reaction where you've got A going into B. And so when you're writing the rate law for this one, we are just first considering rate. Rate for this is going to be given as the change in the concentration of A divided by the change in time. Now, whenever we're talking about the rate of a reactant, because a reactant is always disappearing, you always put a negative in front. Very much important, because a reactant is disappearing. It is forming products. We don't want the rate to be negative. That's why we multiply by a negative always. Now, this can also be written as rate is equal to, instead of using just change delta, we can use D. So we can say dA divided by dt. So this is telling us a change in concentration of A over the change in time. Now, an equation that expresses the concentration of a reactant as a function of time is what we call an integrated rate law. So we looked at a differential rate law, which tells us our rate relates to concentration. Now, an equation which expresses the concentration with time is what is called an integrated rate law. Okay. Now we're going to consider some different orders. All right. So let's say we are talking about, let's start with the first order. Before we start with the first order, let's start with the zero order. Okay. So for a zero order reaction, how do we determine the rate? So rate is given by the change in concentration, of course, back from what we said if we have got A going into B. We know that rate is given by change in concentration of, let me not use now delta, let me use D. So we are saying if A is going into B, the rate is given by negative dA, that is the concentration of A, over dt. Now for a zero order reaction, when we want to write the differential rate law for a zero order reaction, differential rate law is given by K. You get the concentration of the reactant. Because we're talking of zero order, it will be raised to the power 0. So we're going to relate the differential rate law to just the rate to be able to determine the integrated rate law. And so what we are going to do is we are going to get negative dA. So we are using square brackets because we are representing concentration, over dt. And this should be equal to, because this is rate, this is also rate, then it should be equal to K A to the power 0. So from here we are going to pick it up. So I can remove now this portion and we go on in, we see how it comes about. So we are saying negative dA divided by dt, and that is equal to, we know that A to the power 0 is 1, so this is simply going to be equal to K. Alright, so that means the rate law for a zero order reaction only depends on the equilibrium constant. Now from this I can cross multiply, first removing this negative, taking it to the other side, or dividing by a negative and then multiplying this by what I can see there. And so that is going to give dA being equal to negative K dt. Well, when you have got dA and dt, we can integrate on both sides for this kind of problem like this. So we're going to introduce the integral. So we are going to bring integral this side, also going to bring the integral that side. Now the integral that we are talking about is definite integral. That means it has got limits. Okay. So the limits for this integral, let me just write it somewhere here and also here. So the limits are on the down part. For integrals, we always put the lowest point, and then on the upper part we put the bigger point. So because you are talking about dt, we are talking about the change in time, and so this side what we are going to put is, we are going to put first at time is equal to 0, and then at time is equal to t. So when a reaction is happening at this time, and then at the beginning. So now at the beginning of a reaction at time is equal to 0, we have what is called initial concentration. So that is initial concentration shown like that with a O on top. And then at time is equal to t, we have got a certain concentration which we want to find out. So these are the limits for this integral. And now we go on and integrate. Whenever you are differentiating dA, say you just have an integral and then you have got dx. That means you have got a 1 here. The integral of 1, if you are integrating with respect to x, is going to be x. So now the integral of dA, we are differentiating with respect to a, is going to be equal to what? Is going to be equal to a. Now the upper limit is going to come here. The lower limit comes down here. And that will be equal to, well, at this place we have got a constant. For a constant, we just bring it outside. We're going to bring it outside the integral. And then we're going to have the integral dt. And then the limits, we have got time and 0, because at the beginning time was 0. So now the upper limit, we're going to substitute it first. So we're going to substitute where there is concentration of A, we're going to put the upper limit, which we can see there, that is the concentration of A, and then minus, we are going to put where there is A, we're going to put the lower limit, that is the concentration of A initially, and that is going to be equal to, so whenever you have got, after integrating, you found a number such as say x, then you have got a 2 there, you've got a 1 there. To find the value, you first get the upper limit, where you put where there is x, and then minus where there is x again, you put the lower limit. So that is how you find the value. Well, for the other side, that is going to give us negative k. If we integrate dt, that is going to give us only t. So now the limits, the upper limit is t, the lower limit is 0. And so this is going to give us a concentration of A minus the initial concentration of A is equal to negative k. Where there is t, we are going to put the upper limit. The upper limit is still t. And then minus where there is t, we are going to put the lower limit. The lower limit is 0. Now, if we substitute 0, well, it will be just 0 and it doesn't change anything. And so it will end here. So what I can do is I'm going to take this one the other side. So that will give me the concentration of A being equal to negative kT plus the initial concentration of A. Okay, the initial, I'm going to write it outside. The initial concentration of A. So this is the integrated rate law for a zero order reaction. So if you want, you can master it. If you want to know how to get it. So as we can see, it is in the form y is equal to mx plus c, where y is representing the concentration at a certain point, and then the k here is representing the gradient, and then the t is representing the x value, and then what else? The initial concentration will represent the y-intercept. And so if we are sketching such a graph for a zero order reaction, so for a zero order reaction is going to look like something like, so we can see that this is negative kT. So the meaning of negative here is the graph is going to be going in the opposite direction. It will be reducing. To be reducing like that. Why? Because k is the gradient and the gradient is negative. And then this, as we can see, is the x value. So the x-axis has got x. The y-axis here is this one, which has got the concentration of A. Okay, and then the intercept here is the initial concentration, which is that point. So this is the graph of the zero order reaction. Well, another thing that we need to determine from a zero order reaction is actually the half-life. Now, how do we determine half-life? What is half-life? So let's keep the integrated rate law, and now let's talk about half-life. So half-life is the time taken for the concentration to reduce by half. Imagine at the beginning you had 10 molar as the concentration, and then after 2 hours the concentration is now 5 molar. So the half-life for this reaction is 2 hours. That is because for it to reduce to only half of itself, it took 2 hours. That is what is called half-life. And so the half-life for a zero order reaction, so half-life, we are saying the concentration at a certain time, if it is equal to half of the initial concentration, that time taken is what we refer to as half-life. So this is the concentration of something at a given time, let's say after 2 hours. So let's say you have got 20 molar. Okay, now the concentration of this becomes 10 molar after a certain given period of time. So that time is what we refer to as half-life. Why? This was the initial concentration, it reduced by half, just divided by 2. So this is the initial concentration, we are dividing by 2 to give us a certain concentration which is equal to this one. So the time it takes is what we are going to refer to as the half-life. Alright, now let's proceed. Of course, we know that the concentration at a certain time, which is equal to this one, this is a concentration at a certain time. Okay, so the concentration of at a certain time, we can replace this portion. So if we only know the initial concentration, we can determine the half-life. So where there is a concentration at a certain time, we are going to replace, because we know that AT is equal to this portion. So we are going to go on and replace negative KT plus initial concentration. So all I've done is I've replaced with that, and this should be equal to half the initial concentration. Okay, in that manner. So at this point, what I can do is I'm going to take this one the other side, it will become positive, and then I'm going to bring this one this side. So that will be the concentration initially minus, this becomes minus because it's crossing the equal sign, half concentration of initially is equal to, this becomes positive when it goes to the other side, that is going to be positive KT. And so if you subtract 1 minus half, we are going to get a half, I mean. So if you subtract this and this, you are going to get a what? Half initial concentration, and that is going to be equal to KT. So to remain with the value for T, this T is what we are calling as half-life. So to remain with the value for T, we are going to multiply this, we are going to divide both sides by K. And so T is going to give us the initial concentration of A divided by, we can also write this 2 down instead of putting it there, so 2K. So this is the equation which gives us the half-life of a zero order reaction. Actually, the half-life of a zero order reaction only depends on the equilibrium constant and the initial concentration. So we also need to know this one. Alright, let's consider second order reaction. Before second is first order, because this is a zero order.